thermodynamics, right? This idea that you can't have a perpetual motion machine, that that the universe sits in between of all of these energy transactions and always kind of takes a cut, right? So we can't always get what we want, right? So if we're evaluating something that already exists in real life, like you're looking at this turbine and it's operating, answering these three questions is probably enough, right? Where do we draw the control volume? What happens to the mass? And then what happens to the energy, right? But if we're designing something that's never been done before, then you might have to ask yourself if the process you're looking at is possible, because like we saw before, just looking at conservation of mass and conservation of energy will tell you what will happen if a process is possible, but it doesn't really tell you if you can actually do that thing, right? Because like we said last class, we could imagine a case, right, sitting around a campfire where we capture all the mass that leaves and all the heat that leaves, and we put that back into the system, but we don't kind of get back to these logs, right? So just because you pass continuity or conservation of mass and conservation of energy doesn't necessarily mean something can happen, right? There's something else we have to check out, right? So particularly when you're designing a process, right, or you're trying to figure out if, you know, something you saw on a late night infomercial is actually possible, right, then you might want to do a second law analysis, right? Because it's the second law that tells us whether or not something is possible, right? It tells us that to satisfy the first law, basically there's a natural direction that a process wants to go. And that natural direction points in the direction where the entropy of the universe is always increasing, right? And that's basically what the second law tells us, right? So in the second law, we're going to have to look at this rate version of the equation, particularly if we're looking at open systems, right? Where we talk about the rate at which entropy is being stored in the system. We know that somehow heat transfer is related to entropy generation. There's some entropy that's coming into the system with the mass, entropy that's going out of the system with the mass, and then this new term, right? This entropy generation term, because unlike conservation of mass and conservation of energy, entropy is not conserved, right? It's always increasing, and that's represented by this sigma dot term, right? This is our entropy generation rate. So we know that for real processes, right, something that can actually happen in the universe, entropy generation will be positive, right? That means the rate of entropy generation is also positive. Now, we could maybe imagine a system where the very best we could do, right? So the limit of what we could approach is if we got that entropy generation term down to zero. This is actually impossible, but it sort of puts the border, the limit on what the possibilities are. Anytime you get an entropy generation rate less than zero, entropy generation rate being negative, it either means you made a mistake in the math, or this thing that you're trying to do is not possible, right? In last class, we looked at this for turbines and pumps, right? Cases where we didn't have this heat transfer term. Now, for me, if I'm going to mess up this equation, it's that heat transfer term that's probably going to get me. So today we're going to take a little bit of a look on how to deal with the heat transfer term, and then we're going to sort of look at the second law in a new way, right? So one of the other things that we talked about last class was that instead of drawing TV diagrams, right, now we're going to draw TS diagrams. So specific entropy is on our x-axis. The good news is that it follows all the same rules of a TV diagram. So here, if you've got a vapor dome, right? So if you're dealing with water, you still have a vapor dome, right? And you still have a constant pressure line that moves up as you go left to right and stays flat under the vapor dome. Now, what I've done, and we'll become more familiar with this particular device over here, but this is kind of like the most basic form of a coal or nuclear fired power plant that you could have. It's got different open system components in it: a pump, a boiler, a turbine, and a condenser. We don't have to know too much about that yet. But what we do know is that we can do a first law, a second law, a conservation of mass analysis on each one of these components individually. In last class, we looked at the turbine and we said, oh, the benefit of this TS diagram is that if I had an ideal turbine, we saw that delta S across the ideal turbine was 0. So if I was dealing with a turbine or a pump, I would have a vertical line, either up or down, depending on whether the pressure was decreasing in a turbine, or the pressure was increasing in a pump. Right? Now, the nice thing about that, right, is because Q dot was equal to 0. So that got rid of kind of the most difficult term in that equation. Right? But then I said, well, I was talking to my brother and I told him, the one thing that I know about the second law is that the entropy in the universe is always increasing. And my brother pointed me to, this, he's a biochemist, right? So they do this class called physical chemistry, which is one of the hardest classes in their program, right? Which is also thermodynamics, basically. And he said, well, that's not true because you can see a condensation reaction, right? So in the condenser, we go from a vapor down to a liquid, right? And we can see pretty clearly, right? This is a TS diagram. S is decreasing. Right? S is increasing everywhere else on this graph, right? So this is a real pump, so S is increasing. The boiler, certainly S is increasing. We're moving to the right, right? The turbine down and to the right. But then this condensation reaction, right? Entropy is decreasing. So how can that be, right? And I told my brother, you have to look at the universe. It's not the entropy only in your system that will always increase, because clearly that's not the case. Obviously, we can condense water, right? It happens every day, right? But even when we're condensing water, the argument from the second law is that the entropy in the universe will increase. And that happens because of this heat transfer term, right? So even though the entropy, the specific entropy of the fluid is decreasing, I'll show you that the entropy of the universe is still increasing. Right? And we'll do that with this example. I'm just going to go through this one on the PowerPoint slides because I want to make sure we get through the rest of the material as well. But this is a condenser, right? So water comes in, right? Just like in our figure there, it comes in as saturated vapor. So it's right at the right-hand side of the vapor dome. The quality is equal to 1. So if it's, if it was 1 atmosphere, right? Then it's still at 100 degrees, but it's all vapor, right? And then it goes out as a saturated liquid, right? So now the quality is 0. Again, still at 100 degrees, but we've condensed all the vapor, right? So the vapor quantity, there's no vapor in our system when we leave. We're just liquid water, right? We have a temperature, and we also have our temperature on the outside of the system, right? So this is, inside the system, this is going to be 100 degrees the whole time, right? But outside the system is 40 degrees Celsius. So it's a little hotter than it was, say yesterday when I was walking around, but not that much hotter. We were at least here getting up to 35 or 36. I don't know what that is in Fahrenheit, but probably 90 or so. Pretty hot, right? So this is funny because I guess when I moved here, my phone is still set on Celsius. My car too. So we had to sell one of the cars when we moved here, after we moved here for a little while because we had our third kid. We had to get a van. But my cars I bought in Canada, right? So the speedometer doesn't look like the speedometer you're used to. It has miles per hour on it, but they're small numbers on the inside. And I got kilometers an hour on the outside because I'm wearing my Canada Day shirt here, right? Even though it's not quite Canada Day yet. We got a couple of days till the 1st, right? So we're going to do here an open system analysis on this condenser. And I'm going to show you that this is possible, that the entropy in the universe is still increasing. Right? So the first thing that we do is we draw our control volume. Right? And we can do conservation of mass here. Right? So dm by dt is equal to the sum of m dot in minus the sum of m dot out. Oftentimes we'll just do it in our head when it's like this. because we're going to be at steady state. We're going to have one inlet and one outlet. So the mass flow rate at state 3 is equal to the mass flow rate at state 4. I don't remember if I put that in the presentation, right? So we're going to try to find first the symbolic solution, and then we're going to go through the numbers, and I'm going to show you that entropy is still increasing here, right? So here's conservation of mass, right? We know that dm by dt is equal to the sum of all the mass flow rates in minus the sum of all the mass flow rates out, right? But in our system, we're going to say that it's at steady state. So anything in any of these equations by dt goes to 0. Because this is like, how is the mass in my system changing with time? Well, we're at steady state, so nothing is changing with time, right? So that goes to 0. Because we only have one inlet and one outlet, we get rid of those summation signs, right? So our equation here is just that the mass flow rate in is equal to the mass flow rate out, right? Or that there's only one mass flow rate and I can just call it m dot if I want, right? I don't have to differentiate between the inlet and the outlet mass flow rate because they're the same thing, right? And the problem told me, you know, for ease of mathematics here, that it's 1 kilogram per second. So now we're going to go to the first law analysis, right? So the first law, right, we're going to have to make a couple more assumptions, but we've already assumed that we're at steady state, and we've already assumed that we're one inlet and one outlet, right? So those things already go away, right? There's no fan blades inside my condenser. So we're going to say that this is passive, or that the power term here is much smaller than the heat transfer term. We're going to neglect the change in elevation between the inlet and the outlet, and the change in the velocity between the inlet and the outlet, because we're going to say that the change in the potential and kinetic energies are not that important. And when we do that, we get this equation that hopefully is starting to get a little bit familiar. Right? Remember, if we have a W dot term, it would be m dot times hi ho, right? H in minus H out if we're trying to find work, right? But now, because we're trying to find heat transfer, it goes the other way. But you can always just get that from the first law. So again, my advice to you on exams is always write down the first law, cross out the terms, because that demonstrates your understanding, and then you'll get the right answer, right? Because I could give you a problem on the exam where there was a fan blade in here and you knew something about the work, and then you have to try to figure it out, right? So just because these are assumptions that we often make doesn't mean that they're assumptions that we'll always make, right? So we know the mass flow rate, it was 1 kilogram per, I can't remember, per second, I think, but we don't know either of the specific enthalpies, right? So we have the symbolic solution, but we don't have a numerical solution yet because we haven't fixed the states, right? So we can do that now. Now, here the states intentionally are fairly straightforward to fix because we're at the same pressure, right? This was a constant pressure process. And in one case, we have saturated vapor, and in the other case, we have saturated liquid, right? So here, right now I'm trying to fill in, right? So we know we're at 100 kilopascals, right? Or 0.1 megapascals, which is also 1 bar, right? And we're going from saturated vapor to saturated liquid, right? So H is just going to be, H3 is going to be Hg, right? And H4 is going to be Hf, right? So I can fix my state, right? So first I can look at state 2. Here I go to my tables, right? So this is, I knew the pressure. So I go to table A3 where I know the pressure. Here I'm going to take the line for, or the row for 1 bar, right? And I can pull off Hg because here my quality was 1, right? So here I can pick up Hg, and while I'm here, and I know I'm doing a second law analysis, I might as well pull off the specific entropy as well, Sg, and I'll fill in my table, right? So these I just read off the graph, right? Or the table, sorry, right? So I put those in here. Right, now I'm going to do the same thing. And the nice thing, because this is a constant pressure process, there's no interpolation here because the quality is 0 and the quality is 1, right? I'm actually going to use the same table, even the same row, right? It's just my quality has changed from 1 to 0, right? So now I'm going to take HF and SF, right? So the one thing that I'll caution you, right, particularly when you're taking the specific enthalpies here, remember that this column for HFG is here, right? So HFG, I don't think you'll confuse it with HF because the HF values are all really low, right? But HFG, if you're going pretty quick, you might accidentally write down HFG instead of HG. But remember, HFG is HG minus HF, right? That's something that we often have to use when we're doing the quality equation. But here it doesn't matter because our quality is 0 and 1, so we're at sort of the limits, right? So we can just take HF and HG. So now I'm going to take these two numbers, put them into my table, and now I fixed all the states, right? So that's good. So I could, if I wanted to, go back and find the heat transfer, because that's when I started to fix it. Remember, I knew that Q dot was equal to M dot times H out minus H in, right? So now I know H out and H in, so I can try to find H, or I can find the symbolic solution for the second law, right? But first, what I'm going to do here is I'm going to find a numerical value for Q dot, right? So I've got my equation, which I already worked out from the first law, and I fixed my states. Right? So now it's just a matter of putting everything in and hoping I don't fat finger my calculator. So I don't know about you guys, but I'm really good at putting numbers wrong in my calculator. So that's why one of the reasons I like to keep symbolic solutions for as long as I can, because like I said, I'm just really good at messing it up, right? Especially in a test, right? There's pressure situation. Maybe I don't go over it as often as I should, right? And then I get the test back and I'm like, what a stupid thing to do, right? So here, remember, this is H out minus H in, right? And going in, we had vapor, and coming out, we had liquid. So the energy stored in that mass went down by a lot, right? So here we have 417 minus 2675. So this is a negative number. Now, does that make sense, right? Because hip to win tells me that heat in is positive, right? Which must mean that heat out is negative. But again, we're talking about heat loss here, right? Because we're condensing. So we had this energy, or this energy that was stored in vapor, right? And then it went to a liquid, right? So that must mean that it's cooling off, right, to condense. So this does make sense. Heat has to be leaving my system for us to condense, right? So it does make sense. Heat out should be negative. So this is a negative number, and that makes sense, right? So that's good. Now I know Q dot, right? So now I've done the first law part of the problem. So this is, again, all this is really telling me is what would the heat transfer be if this process was possible? Now, we've all seen water condense, right? Or at least seen the evidence of it, right? As you, maybe you squeegee water off your car window, right? Or you see the dew on the grass, right? We all know that condensation is possible, right? But I want to show to you, right? I want to try to build up your confidence in this equation for the second law, right? Because maybe you're like my brother and you're like, this doesn't make any sense because the entropy here is obviously decreasing, right? So we went from 7.36 kilojoules per kilogram Kelvin down to 1.3 kilojoules per kilogram Kelvin. Entropy decreased, right? In the fluid, but not in the universe. And we'll see why, right? So now we want to ask ourselves, is this process possible? We want to go through the second law analysis here. So again, we write down the base level of the equation. We've already made some assumptions here. We know that the system is at steady state. The temperature, or that there's only one inlet and one outlet. Now, the difference between this condenser and the turbines and pumps that we talked about last class is that this system is not adiabatic, right? That this heat transfer term sticks around, right? And this is one of those spidey sense, hair in the back of your neck kind of things, because this term is tough, right? There's two things I got to remember about this heat transfer term. One, the sign is still hip to win. It's the same magnitude, same sign as what you'd get from the first law. But the second thing, the thing that people typically make mistakes on in an exam, is that this temperature on the bottom is not a temperature difference, right? And anytime you have an equation that has a temperature that stands alone, that's not a temperature difference, you have to use absolute temperatures. It's got to be Kelvin, or if it's an imperial problem, it's got to be Rankine, right? So here, our equation simplifies to this, because what we want to solve for is this sigma dot term, right? So I isolate sigma dot, I move all the other stuff to the other side, and I get negative Q dot surroundings over temperature of the surroundings. Oh, that's the other thing people mess up here. So first, you need the absolute temperature, but this is not the temperature in your system, because this heat transfer term is really about what's going on with entropy outside of our system, right? It's what's going on with entropy in the rest of the universe, right? We know that the entropy of our fluid is decreasing, but it's doing that and it's losing heat. So, the rest of the system is gaining heat, right? So if there's a bunch of air around our heat exchanger here, it's being heated up, right? And we know that as that thing is heating up, it's gaining entropy. So this is really telling us what's going on in the rest of the system. So I've got to use the temperature from outside of my system, right? Technically, it's, I think, the temperature on the boundary, right? But usually we use the temperature outside of the system in this analysis. So it's got to be, it's not the 100 degrees inside the system, right? It's whatever we said, 40 degrees, but even that's not right because we got to add 273 to it, right? So here, right, we can solve for sigma dot. We know now Q dot, right? Now remember, this is negative Q dot, right? So here, if we did an accounting here, right, we don't know sigma dot. That's the thing we're trying to figure out. We did our first law analysis, so we got Q dot, right? We know this temperature. I got to pick the right temperature. It's the temperature outside my system, right? And I got to convert it to absolute temperatures. I know the mass flow rate, and I fixed the state, so I know these specific entropies. Now, if I didn't do the problem numerically before, there's no reason I can't. So let's say if this was on a test and part A was do the first law, and you for whatever reason you maybe couldn't fix the states, you couldn't get to a number. Ideally, you'd get a number, but even if you don't, you can still demonstrate your understanding on this part, right? Because you can write down the second law, you can make some assumptions, and you can now get to this part, right? And even then, you can make up numbers to show that you know how to deal with these things, right? So if I was in a case where maybe there's 3 minutes left in the exam and I don't have time to fix all these states, right? I would write down this equation, right, after my assumptions, and I would put an arrow here, and I say that, oh, I know this has to be the temperature outside the system, and I know it has to be in Kelvin, right? So even though I don't know the number, I'm demonstrating my understanding, right? I know that this is still hip to win over here, right? I could write that down, right? So here we can put our numbers in, right? So here we had to take 40 degrees. That's the temperature outside, plus 273. Again, when people make mistakes in second law analyses, it's because of this, right? This term, because this temperature term is tough to put in there, right? So don't make that mistake on the exam, right? We put this in, we'll check our units, right? So we know that on the left-hand side, it's kilowatt per Kelvin, right? And then here, right, we got the kilograms cancel, right? And I get kilojoules per second Kelvin, but kilojoules per second are kilowatts. So it's also kilowatts per Kelvin. So I'm adding apples to apples here. I don't have to do any kind of a unit conversion, right? And if I do this, we can see from this part, right? This part that's telling me about the entropy change of the mass that's in my system, that is negative, right? But the entropy change in the rest of the universe is positive, and the magnitude of the entropy in the rest of the universe, right? It's increased more by the decrease of the entropy in my fluid. So on the whole, I get an entropy generation rate of 1.15 kilowatts per Kelvin. So I'm still getting a positive entropy rate, right? This is another thing where if you can't finish this problem, right, you still write down, oh, if sigma dot is positive, then it's possible, right? If sigma dot is 0, then it's ideal. And if sigma dot is negative, then it's not possible, right? Because you still want to demonstrate that you understand that thing, even if you get bogged down in the math or something. Does anybody have any questions about this example before we kind of go on to looking at the second law in a different way? All right. Right, so because this is bigger than 0, then this process is possible. So this is how we do like a second law analysis. And you should probably expect to have to demonstrate your understanding of this when we get to the second exam. So that's one way of looking at the second law, right? We can look at it and do this open system second law analysis. But there's another way that we can use the second law too. It's kind of a versatile tool, right? So we talked about looking at just the condenser, right? And this is then an open system, right? But I can shift my point of view so that I'm not looking just at the condenser, but I'm looking at all of these components, which are kind of, linked together in series, right? So each one of these components is an open system, but like the outlet of this one is the inlet of this one, is the outlet of that one. It's like a daisy chain here, right? It all goes around and around and around, right? So if I broaden my focus enough, this becomes a closed system, right? Now, this is what we call a heat engine. Like we're finally there, right? Thermodynamics, right? The whole purpose is this energy exchange. We're trading in heat for work, right? And that's what a coal-fired power plant does, right? The input is heat, right? And we change that heat that goes in from burning coal or having a nuclear reaction, right? And we turn it into net work, right? So there is one of the things that we like about coal power plants, right? Even though they have negatives, right? Which we're certainly trying to address, right? But here, the pump, the reason that we condense the fluid, right, is because it doesn't take much energy to increase the pressure of a liquid, right? But we get a lot of energy out from decreasing the pressure of the vapor. So what happens here is the power produced by the turbine is like going to be 100 times greater than the power that we put into the pump. So on net, this machine, right, this heat engine produces power, right? And that's good because as humans, we sort of have this insatiable thirst for power, right, for energy, right, for better or worse, right? So this is called a heat engine, right? And that's the whole purpose of thermodynamics, right? Thermo, heat, dynamics, work, we're turning heat into work, right? So there's different ways to think about the second law, right? And when we're thinking about it on a whole system like this, we can think about it at kind of a higher level than just doing the mathematical analysis of an open system, right? So these names may or may not, you might not recognize the people here, but you've heard of Kelvin, like the temperature scale, right? Thomas Kelvin. Max Planck, maybe in physics classes, you've heard of Planck's constant, right? So these are, pretty important people for the foundation of things like physics and thermodynamics. And what they said was, I kind of hate the verbal, right? Just like before, but I'll read it, right? It is impossible to construct a device which operates on a cycle and produces no other effect than the production of work and the transfer of heat from a single body, right? I don't know if you had to read like, A Tale of Two Cities or something when you were in high school. There's a lot of words in there that maybe didn't need to be in there, right? If you haven't read it, the end of it is beautiful, right? The first 95% of the book is pretty boring, but the last like 5% is, I don't know, I thought it was pretty beautiful. So I'm not a huge like Dickens fan or whatever, but I did like the end of that book. I didn't so much like, but I kind of had to go through the boring part, I think, for the end to be, like I said, as beautiful as it was, right? But it's not English class, right? So what they're saying here really, I'm going to show in a picture, right? So what they're saying is that, yes, we can make a steam engine, right? And a steam engine means we're burning coal and we're producing work. But if you don't have a heat sink, your engine will not be able to run for a very long period of time. I hope this has never happened to you, but sometimes when you're driving down the highway, you see somebody with their hood up, right? Dan was talking about his brother in Arizona. I'd imagine this happens in Arizona, maybe more often than it happens here in New York, right? But maybe their radiator failed, right? And the radiator is the heat sink of your engine, right? It's cooling the thing down, because if it just keeps getting hotter and hotter and hotter and hotter, eventually it's going to fail, right? So Kelvin and Planck are telling us, yes, we can take heat in and turn it into work, but the universe takes a cut, right? It's not perfect. We can't turn all of the heat into work. Even in the ideal case, we still have to cool the engine down, right? So yes, we can turn heat into work, but some of it will be lost, right? And that's kind of this is the downside of power generation, right? There's a lot of great things about things like the Industrial Revolution and us being able to generate lots and lots of power, right? But one of the downsides, and there's more than one downside, is that every way we found to generate energy has some kind of environmental impact that's not great, right? So we're going to try to learn about how to increase efficiency, right? We're going to try to make it so that we're losing as little heat as possible. But even in the best case, we're going to see that we can't turn all of this heat into work. Some of it goes into cooling the engine down, right? So there's always a loss, right? So that's what Kelvin and Planck told us, that if you're not cooling your engine down, then you're sitting on the side of the road with a water bottle trying to, hoping that your engine didn't blow up, right? So what does this mean, right? So this is a heat engine, right? We're getting heat in and we get work out. But what do we know about, we can think about this as net, right? So Kelvin and Planck told us, yeah, you can get work out of this thing, but you also have heat that's coming out, right? You have to cool your engine off, right? So this is a closed system, right? And we know about closed system energy balances, although we didn't look at it this way, right? When we were talking about closed systems, we did elapsed time format where it was delta E is equal to Q minus W. But we can make this look like the open system version that we use, just with no mass flow rate terms, right? So that dE by dt is equal to Q dot minus W dot, right? Now, if this is at steady state, right, our power plant's been running for a little while, it's just at its baseline power, right? Then what happens is that the net heat is equal to the net work, right? So this net work that we get out is equal to the heat in minus the heat out, right? Because that's what the conservation of energy tells us, right? We can't just create energy out of thin air, right? So all the inputs have to equal the outputs, right? So I can write net heat as heat in, right? That's positive, minus heat out. Now here in this case, this is talking about the magnitudes. I should write magnitudes here, but this is how they write it in the textbook. So really, if you were using hip to win, you'd say plus, but the Q dot out term is negative, right? So we're going to define something. Now, if I'm on your committee for your senior design project, you might talk about, we made this product more efficient, right? And my hand will shoot up and I will say, what do you mean by efficiency, right? Because in thermodynamics, there's lots of different kinds of efficiency. And I think that colloquially, which is always a hard word for me to say, efficiency means kind of like goodness, like we made it better, right? But efficiency is the thing, right? It's generally like a percentage, right? So here we have some energy coming in the form of heat, and we have some work that we're producing, right? So how much of that heat did we turn into work? Energy, particularly when we're talking about thermal efficiency, if we're talking about a heat engine, right? So that means how much heat So the energy that we put into the system, right? We had to burn a bunch of coal to make heat. But how good was that heat? How much of that heat did we actually turn into work? That's our numerator, right? Now, generally, we're going to talk about thermal efficiency as being the desired energy effect, the thing that we're trying to get, divided by the cost that we had to pay to get that thing to work, right? So if we're talking about a coal power plant, right, then the desired energy effect is that mechanical power, right? That spinning shaft that we can attach to an electrical generator and make power, right? And then the energy cost is that we had to burn a bunch of coal. We put heat in. So it's not net work divided by net heat, because then it would always be 100%. It's net work divided by heat in. But we've already established that for closed systems at steady state, the net work is also equal to the heat in minus the heat out. And then we can divide that by heat in. I can simplify this a little bit if I want to, right? And I can make this 1 minus Q dot out over Q dot in. Now, what Kelvin and Planck told us was that there is always a Q dot out, right? So this is the thing. Efficiencies are percentages, and it's not like playing football or hockey or something where you can give 110%. Your efficiencies can never be more than 100%. If you do an analysis like this and your heat engine has an efficiency of 110%, it means that you made a mistake somewhere in the data that you were recording or in the math that you were doing. It's impossible to have an efficiency more than 100%, because that would mean you're producing more energy than you put in, right? And that's just not possible, right? Now, there's another special trick that can happen when we have so this equation is always true, provided that we put absolute values here again, right? Because the Q dot out is going to be a negative number, right? Now, there's a special trick that we can do for what we call a Carnot engine. Now, maybe you've heard of this term, maybe you haven't. It's fine if you haven't. Again, this is named after a person. What happens is if you have an ideal engine, right, or an ideal, we'll talk about refrigerators and stuff too, then what you can do in this type of analysis is you can change a ratio of heat transfers or a ratio of heat transfer rates with a ratio of temperatures. So if and only if you're talking about an ideal engine, then you can define this ideal thermal efficiency, that's the best thermal efficiency you could ever possibly get, as 1 minus the temperature that you're communicating with, right? The temperature outside your system, minus the temperature at the inlet of your system, right? So the temperature where you're adding heat. So a couple things that are important to note about this slide. First, this engineering decoder ring thing of Carnot means ideal, right? So if you're talking about a Carnot engine, that's like engineering code for an ideal engine. The other thing is, from a first law analysis, we can get that your actual thermal efficiency is 1 minus the heat transfer you lose minus the heat transfer you gain, right? So the maximum would be if you didn't lose any heat, which we know is not possible, the maximum you could get to is 1 here, right? But, we're going to have something less than 100%. Oftentimes, if you can get to 60% with a heat engine, that's probably pretty good, right? Although, of course, it depends on what your system is. But then you can compare your actual efficiency to your ideal efficiency. This is one of those tooth fairy things. There's no such thing as a Carnot engine. It doesn't exist, right? But it's helpful to know what you're shooting for, because let's say you have your efficiency of, let's say it's 52%, and you feel like, oh, that's pretty bad. But then you go and look, and the maximum efficiency you could get given your temperatures is like 55%, then you're actually pretty good, right? So it's nice to know what you're comparing to. And in thermodynamics, when you're talking about heat engines, you're not comparing to 100%. It's virtually never possible. You'd have to have a temperature of absolute zero over here to get to 100%, right? And I mean, to do that, then you're also you're consuming a lot of power to do that. Right, so here we can check the units here. So thermal efficiencies, these are not percentages, they're per unit values. So they only go between 0 and 1. You could multiply them all by 100% if you wanted to, right? But just to check the units of both of these things, right? So here for this ideal efficiency, it's 1 minus temperature over temperature. Notice that neither of these are temperature differences, which means that they have to be in Kelvin or in Rankine, right? But because they're the same, if they're both in Kelvin or they're both in Rankine, then they're going to cancel out. It will be a dimensionless quantity, and you'll have 1 minus something less than 1, right? And you'll get your maximum efficiency. The same thing here with the actual efficiency, 1 minus Q dot out over Q dot in. Q dot out is going to be whatever your heat loss is, right? Something more than 0. That's what Kelvin and Planck told us, divided by however much heat goes in, right? So again, this will be some fraction that's less than 1, and your actual efficiency will be 1 minus whatever that fraction is. So, right, so we know that the ideal efficiency has to be bigger than the real efficiency, right? Because otherwise, right, the ideal is the best possible case. So if someone is telling you that the efficiency is better than the best possible case, it means that they're wrong, right? Whether they're intentionally wrong or not is a different story, right? But that's a kind of question that you could see on a multiple choice part of a test or something, right? Is like, is this thing possible when somebody tells me that the efficiency of this thing is 65%? And then you calculate the Carnot efficiency and you find it's only 55%, so it's not possible to get that 65% efficiency. Right, so this is just an example, right? So here we've got temperatures, hot and cold, but they're given to us in Celsius, right? So the spidey sense should be tingling. And we're told what the heat transfer in is. What's the maximum work that we could get out, right? So in order to do this, right, the maximum work, right, we can find the maximum efficiency, right? That's 1 minus T cold over T hot. But we got to convert both of those things to Kelvin. So we add 273, right? Here we see our maximum efficiency is 24%, right? So if I told you that the efficiency of this engine was 24% before we saw this, you'd probably think, wow, that's pretty terrible, right? But it's actually the best it could possibly be given these temperatures, because these temperatures are so close together, right? But we also know that the thermal efficiency is the power divided by the heat in, right? And the ideal thermal efficiency is the maximum amount of power that you could possibly get out of this engine divided by the heat transfer rate in, right? So you'd see this would be 24% of this Q dot in, or 24 kilowatts. This is another cool thing about having simplistic models like this. So we won't go through it too deeply, right? But I'll tell you that there's a couple things that you could figure out, right? If you wanted to increase this maximum thermal efficiency, and it's 1 minus T cold over T hot, you've got two levers, T cold and T hot, you could tell me two things that we could do to improve the maximum thermal efficiency here, right? But we won't go into it. We'll talk about it a little bit later. But that's kind of the nice thing about a simple model like this, is it shows you what your variables are, right? So how could we get a better thermal efficiency, right? So that's heat engines, right? But at around the same time, right, we started to think about things like food preservation, right? So there's this other guy, right? He looks like evil Santa Claus or something over here, Rudolf Clausius. He said that it's impossible to construct a device which operates on a cycle whose sole effect is the transfer of heat from a cooler body to a hotter body, right? This is, again, these words are really confusing. So here's the picture. So what Clausius tells us is that we can make a machine that moves heat from a cold place to a hot place, right? Something like an air conditioner or a refrigerator, right? But that thing can't also be producing power, right? So even though it's taking heat in, we can't use this as an engine. That's not possible. It can't even break even, right? Because what we're doing here is we're making a machine where the cold half is colder than our cold place, and then what happens is the hot half gets hotter than our hot place. You may have noticed that with both your air conditioner and your refrigerator, you have to plug something in, right? Because you've got to run a compressor. So these things are not producers of power. For this to be possible, you have to consume power to do this, right? So we can make heat run in the direction that it doesn't want to run, or at least we can make it look like that, right? Even though that's not how it's working locally. But in order to do that, there's a price. And the price is that we're adding power to the system. Right, so there's two different devices we'll look at that do this, right? One is called a heat pump, and one is like a refrigerator or an air conditioner. They're really the same thing from like a physical point of view, except your point of view is different. If you're talking about a heat pump, then you're sitting in the hot reservoir, the place where heat is being pushed to, right? This is like an, it works better, I think, in milder climates than what we have here in upstate New York, but you can use this to heat your house. But again, I think it works. I think you don't see that a lot up here. We normally have natural gas furnaces, but in more temperate places or more, where it doesn't get as hot, then this is a good way to heat your house, I guess, right? Here we're putting work in, right? So we're going to think about this conceptually, kind of like a heat engine, right? So what a heat pump does is it pumps heat into the hot place, right? This is the opposite of like what happens in real life, right? Like maybe if you're like me, when you're growing up, your mom would yell at you, you got to come for dinner because your dinner's getting cold, right? Hot things tend to get cold. Cold things tend to get hot, right? But here we have a machine that does the opposite, right? So Clausius tells us we can't build a heat pump that doesn't consume energy, right? That you don't have to plug into the wall or a solar panel or a wind turbine or something, right? Something that's generating power. Here we're going to talk about something called a coefficient of performance. Coefficient of performance is kind of like efficiency, but we don't use the word efficiency here because coefficient of performance is always more than one. And efficiency is a percentage or a per unit value that can only go from 0 to 1. So we call it this coefficient of performance. But conceptually, it's still the same thing. It's going to be the energy effect that we want divided by the cost that we use to achieve that energy effect. So in a heat pump, we're sitting in the hot place and we're trying to heat it up, right? So for a heat pump, the energy benefit is heat going into the hot place, or Q dot on the hot side of the system. The cost is that we have to plug this thing into the wall and it's running some kind of compressor or something, right? So that it's consuming power. So here, our coefficient of performance is Q dot hot over W dot net. We can use that same idea that we used when we were talking about heat engines, that the net work or the net power is equal to the heat transfer rate on the hot side minus the heat transfer rate on the cold side. And if we do that, then we can also talk about a Carnot coefficient of performance or an ideal coefficient of performance where we turn this ratio of heat transfer rates into a ratio of temperatures. My advice to you is always going to be, if you're trying to figure out Carnot efficiencies or Carnot coefficients of performance, always use absolute temperatures. But here you can see in the denominator, it's a delta T. So Celsius and Fahrenheit are okay in the denominator, but not the numerator. But if you just want to make it so you never really have to think about it, you can just always use Kelvin or Rankine. You'll never go wrong with absolute temperatures. Or at least You won't go wrong with that part of the problem. So a Carnot heat pump is just an ideal heat pump, right? They don't really exist, but they give us a line to shoot for, right? They're the limit of what's possible. I'll just take 2 more minutes here because we can also talk about refrigeration units. Refrigeration units are very similar to heat pumps, except that our point of view is different. So now, instead of trying to heat up the hot place, now we're trying to cool down the cold place, right? Whether it's the food storage area that you have in your fridge, or it's just the volume of your house if you're trying to air condition it, right? So here the energy benefit is the heat we remove from the cold place. Right, so this happens at the cold temperature. Clausius tells us that this can only happen if we're consuming power. So again, here we don't have an efficiency. Refrigerators look like heat pumps in that we talk about something called a coefficient of performance. This is related to, but not exactly equal to, something called a SEER rating, which is what you might see if you're trying to buy something like a central air unit, right? Now the energy benefit here is Q dot out from the cold place. And the energy cost is, again, that you've got to run some kind of power into this system, right? My air conditioner is a big cost in the summertime, right? Because it's running and that, I'm paying for the power that it consumes. But I can make a W dot net into Q dot hot minus Q dot cold, excuse me. And then if I'm talking about an ideal system, then I can go to the Carnot coefficient of performance and have T over T minus T, right? So T cold, because the energy benefit happens on the cold side, divided by T hot minus T cold. So again, this Carnot thing, it's not actually possible, but it's the limit of what's possible. So it sort of gives us something to shoot for, right? It lets us know where the line is, right? And we'll talk about later that just the form of this kind of idealized simplistic model gives us some hints about what we can do to improve efficiency. So that is all that I had for you today. I will stick around for a couple of minutes just in case anybody has any questions. But otherwise, I am finished with the lecture. Thanks, everyone.
I had a question about homework 6.
Yes.
Is homework 6 just the rest of the questions in what is listed as homework 5 in the homeworks 2 through 10 sheet?
Yeah, I think it should be so homework 6 would be the one that's due next Monday, right?
Yes.
Yeah, so it'll be the ones that are related to if you look on the new version of the syllabus, right? They'll be the ones related to the lectures we're having now.
Okay.
Right, but before Monday.
Okay. All right. Thank you.
I think I pushed it to Tuesday actually, right? Because Monday's the holiday, I think.
Maybe.
I will if I haven't yet. I'll double check.
Okay.
Okay.
All right. Thank you.
Yep. You're welcome.
Have a good rest of your day.
Thanks, you too.